Should be working now.
Yes, perfect. Yes. Yeah, you can. Thank you.
Yes, so my institute is working on battery and fuel cell, and my specific lab is working on a battery management system and fuel cell management system, and also management system for electrolyzers. The objective is to work as on the electronic part, the embedded software, and also the algorithms for the state indication of this device, this electrochemical storage device. And the idea more and more is to introduce more and more digital capabilities and also signal processing and also machine learning to be better in terms of accuracy of the estimation of these indicators. So for example, we are talking about the state of charge of the battery, state of power, and state of health, aging, and also for fuel cell, which is about the subject here on this presentation. Fuel cell, the main target is to work on fault detection and isolation and aging prediction. So in fuel cell system for automotive industry, the main challenge at the moment is cost, of course, complexity, but also durability. So the idea is to develop methodologies of PHM, so productive and health management, to evaluate the trajectory of aging and also evaluate the non-optimal operating conditions. So we can talk about faults or non-optimal operating condition. This means that the fuel cell stack, so a fuel cell is an electrochemical conversion system that take as input air and hydrogen and produce water, heat, and electricity. And this system is quite complex and must be operated in a specific range of temperature, voltage, current, and pressure of the gases, so the perfect stoichiometry, and also humidity of the gases. This is very important. So if you are not controlling the system, so at the core of the system, you have the stack. So it's a stacking of bipolar plates with membranes. So in the bipolar plate circulate the fluid for cooling and also the gases that are producing the chemical reaction within the membrane that contains the catalytic layer based on platinum. So this system must be operated with different ancillaries that place the stack in the perfect operating condition. If the operating conditions are not optimal, the performance decrease and also the aging is faster. So all the aspect of this work is to work on detecting that the operating conditions are not optimal. So when I talk about operating condition, it's about flooding, drying, air starvation or hydrogen starvation, for example, and also predicts degradation, predicts the aging. To feedback. Yes.
A problem. The slides are not moving.
Yeah.
Now they are.
Yeah, I'm gonna move. Yeah, it's just the context about our system. Yeah, sorry. And to go a bit deeper in the problem, so we need to detect this fault and also compensate them. And now more and more people are introducing AI algorithms to work on this time series and predict the fault, classify the faults, and also the aging. So the typical trend is to use the data, but in our problem, we have very few data because those systems are very expensive, very complex, and very difficult to set in an experimental setup. And when you are talking about fault and aging, you are talking about a very long test campaign. So the data can be acquired, but they are very scarce. Although deep learning algorithms are really heavily reliant on data. So what we are going to do is that in the past, people develop a lot of complex physics-based model, and those models still are affected by a large error, but they still contain a lot of information, a lot of theoretical information in it. Whereas the real ground data from the field, from the experimental test campaign, are accurate, are true, but are very limited in size and a number of different systems that could allow us to do studies on the generalization of the algorithm. So how do we combine them? We will combine them through physics-informed machine learning. And in physics-informed machine learning or physics-informed neural network or physics-guided neural network, the idea is to combine a data set. So for example, here is one data set about a fuel cell that we acquired in the past. So it's a long data set with aging. So it's about 1,000 hours of operation. So you have aging and also you have fault in the graph below. You have a spike that represents the type of fault and the time of occurrence of the fault. So this dataset contains real data with dynamic operating condition, with dynamic profile. So it's automotive driving profile during a long time on 1,000 hours. But it's only one dataset, and we will compensate this limited size of dataset with a model. For example, in-house in CEA, we developed a specific multi-physics, multi-scale model called Mephisto that you can parameterize from very complex to more 0D reduced order model. And the idea is how to define how we can combine these two models. So first, the model has to be calibrated. So it's a model containing all the theoretical information of the different chemical reaction inside the fuel cells and also all the behavior of the ancillaries. But you have to fit the model to your specific system. So we have a specific procedure with a polarization curve of the fuel cell. So drawing voltage regarding the current at different level of current and different condition to tune the parameters and to identify the parameters of the model. Still, once this procedure is done, we can assess the performance of the model and validate it, but we still have error. So for modeling people, the error is quite nice and it's even quite accurate. But for us, eventually it turned out that it's not enough to classify the fault. Indeed, if you take, for example, a simulated dataset, for example, basic idea is to use the model to generate a simulated dataset, a large dataset, to train your algorithm on it. For example, here, a long short-term memory neural network for the fault classification task. And then you want to test on their experimental dataset, and it's really not working. So, which means that, in fact, when you are analyzing the results, you can see that since the model is quite accurate with low level of error, the error is larger than the distance between classes. So you want to classify your fault. For example, normal here is an optimal operating condition with the correct level of humidity. So no drying, no flooding, and air starvation and nitrogen starvation control the stoichiometry. So here you can see that you are not able on this confusion matrix to classify really the faults. So what we're going to do is we evaluated two approaches on mixing the model with the data-driven algorithm. So here it's LSTM. The first approach is to somehow realize data augmentation. So this means that as input of the neural network, we use the real data set from the real stack system, the real fuel cell system. And also, we use the data coming from the model. So in the model, we have at the output different variables that are not that are hidden in a real system. For example, relative humidity that is computed inside the model. So we use also all the variables that output the model and even the hidden variables. And this allows us to increase dramatically the performance in terms of accuracy and F1 score compared to pure data-driven test or pure simulated training. Second approach in which we believe a lot is very powerful, is based on an evolution of the GAN network, so generative adversarial network. called domain adaptation neural network, working with a source domain. So here in our case, it's a simulated data, and a target domain, which means for us will be the experimental data from the real fuel cell stack experiment. So we will implement this domain adversarial network, and the idea is to adapt, in fact, your data set at the output of the network that will realize the main task. For example, in our case, the classification task. So, for example, we implemented this type of neural network. So you have in green a feature extractor, right? In blue, it's a simple fault classifier based on a dense layer. And in pink, the domain discriminator. So in fact, when you will try, and you design specifically the loss function to take into account all the loss of this different network in a combined way. So as remember that the source domain is simulated data and the target domain is real data. So what we want to do here is not to improve the accuracy of the model and not to decrease the error between the model and the real data. What we want to do is that at the output of the feature extractor, this feature extractor is trained to project the data, source or target, on a space where the classes are aligned and where we got some invariant in the data, in the information that will be useful for the fault classifier. So we want to map at the output of the feature extractor the different class with a good accuracy. And this is done through the combine and opposite training of feature extractor and domain discriminator, where the feature extractor so extract the feature, and the domain discriminator, the task is to discriminate if those features are from source domain or from target domain. So at the end, when it's well trained, the domain discriminator is not able anymore to discriminate if those features are from source or target. And so you can use the fault classifier to detect the fault and classify which is the fault. So, for example, here we can see that on the left you have a source in blue and target in yellow in a 2D representation, and that so the source and target are well aligned. And also on the right, you can see that the classes are well aligned between source and target. Because in our experiment, sometimes when you design not well the loss function, in fact, it can happen that okay, source and target are well aligned, but you lost here in this loss function. You lost if you don't design the loss function correctly with the tree network. You can lose information of the classes. So you align correctly the source and target, but the class are not aligned anymore. Sorry, seems a bit stuck. Can you hear me? Yeah.
Yeah, we can hear. But there is some sort of echo. I don't know why we can't get it off.
Mm-hmm.
Vincent, can you hear us?
Yes.
Okay.
Sorry,
We saw you
I don't know why team is stuck.
We had your slides in front, so there was no problem with that.
Sorry for all these problems. I don't know why it's all stuck. Perhaps if you have some question on this first part, I can answer in the meantime.
Maybe while you're setting up, we can just say a comment from our team side. So we have not here present, but in the teams we have some colleagues with whom we did some aging-related research. So we had all kind of aging measurement and prediction for basically having CMOS aging. But this is also a physics, let's say, a physics-based process. But we did it several years ago, so we didn't have this machine learning aspect there. So I think actually the things that you showed is also very, very valid to the research we have done here. So it would be very, very interesting to try some of these.
And what type of method did you use for combining model and data?
So we had the NBTI aging model for CMOS, and then we were calculating based on different execution profiles how the circuits were aging. And basically, this was based on a physics. It's a physical model, right? So it takes into account the time, temperature, and then also the switching activity of different nodes in the circuit.
Okay.
Yeah, and then so maybe something could be improved there by combining the physics and the machine learning.
Yeah, exactly. That's our goal for many different systems. So in our team, we are working on battery, fuel cell, and also power converters. And we can see that in these three different systems, it's very difficult to have data, so a large amount of data, to really get the power of AI. And so we really need that it's mandatory to use some kind of data. And for example, on power converters, we see that only by constraining a bit the loss on physical equation, it's enough to make the neural network converge better and to reach a better accuracy. So and specifically for batteries, there are a lot of work. Battery and fuel cell, there are a lot of work on modeling, so we can extract those data and make a good choice on the neural network. Sorry, I'm really struggling with the Teams. I got the audio, but it's the only thing that I have. Trying to close everything, but
we still see the. Yes, now it came. Yeah.
Okay.
You can
Perfect.
proceed.
So we had very sorry for this delay. So we use this domain adaptation method, and it was very promising. So if you work only on the data in some kind, so only experimental data, you can have a good classification of the normal operation condition, but it's not what we really want. But you have a poor classification of the other fault. And with the domain adaptation neural network, you have a large increase in the classification confusion matrix and on the score. And on top of that, if you add more faults, so if you increase the number of class to be used, you can see again that source and target are well aligned in the feature space, in the latent space, and also that all the classes are preserved in the feature space, thanks to this joint training of feature extractor, domain discriminator, and fault classifier. So the confusion matrix is quite great, even if we increase the number of class. And also, what we've seen is that it can limit the need for data. Even with our short data set, we can see that that even we can retain only 5% of our data set. So which means that we keep very high result of accuracy and generalization, even if we decrease the number of data. So what it means is that working with a very large simulated data set and with a very small amount of real data through this architecture is enough to get very good result. The second part we are working on the fuel cell is remaining useful life. So degradation estimation, prediction of the aging, and prediction of the remaining useful life. So there are many different physical quantities that we want to assess. So for example, main one is electrochemical catalytic surface area, is the equivalent surface of platinum if you develop the surface of all the platinum particles. And this is decreasing over time when the fuel cell is aging. So this can be a very good remaining useful life indicator. You can also use a voltage at specific level. So the objective is at some point to diagnose, estimate the current level of aging, and prognose what would be the aging, what will be the aging in the future, to retrofit and retro feedback the action variables to control the fuel cell differently, so to extend the lifespan. So if you detect and if you estimate and prognose that you will be on the green path, the idea is to change the control, so the control of your fuel cell, to be on the blue path. And again, we will work on physics-informed machine learning to combine the model that we have in terms of fuel cell and fuel cell degradation with a neural network that is able to hybridize the data on the model. So the idea, for example, and we are working on two approaches. So learn a local model of the voltage behavior. So when the fuel cell is aging, the voltage is decreasing. And what we will do is, okay, to have a certain buffer of points, for example, voltage, current, temperature, and pressure. That's a typical variable that can be used as the input of the neural network, and to predict a small amount of data just after in the future. So, for example, predicts the next step of voltage. And the second approach is long-term prediction. So we have a certain buffer of past time series, past voltage, for example, and we want to predict a long period of time based on the historical data. So what we can do is, okay, again, have a baseline on pure data-driven based approach as a baseline. So pure working on pure data, so recorded on fuel cell. But we have very few. We have seen it on different projects. For example, the Escalate project, that we have very few data. And also, if you really want to assess AI algorithms capabilities, for the generalization is very not enough. So the idea is to work on the hybridization of the data and the model. First idea, of course, is transfer learning. So we will generate a large synthetic data set. We train the first time the neural network, for example, an LSTM or a BLSTM. And then we keep the weight of the network fixed, and we have a second step of training on the small real data set to come to the inference, to use the neural network as an inference to predict the rule. And the second is, as I described for the fault detection, is to combine synthetic data and the real data as the input of the machine learning model. This methodology is a bit worse because you need the data of the model in operation. So somehow you need a certain version of the model in operation embedded in your system, which is not somehow not really wanted. Because the model can be quite complex. And so we got nice result on a specific fuel cell on a data set that we evaluated. So of course, if we are working on short-term prediction, the past time series are in blue, the real future is in green, and the predicted future is in red. And so yeah, if we want to do short-term prediction, so one step, for example, what will be the voltage in 1 hour? One step is 1 hour here. We are able to have very high accuracy in terms of prediction. And if we work on long-term prediction, of course, the pure error is increasing, but we capture really well the trend, which means that with a very limited size of data, historical data in the past, we are able to predict a long period of time, so hundreds of hours in the future. And this long-term prediction can help to get the remaining useful life. So the idea is to have some kind of ping pong between the two, short-term prediction and long-term prediction, to work on the control. So you have a very low-level control with a high dynamic, and higher level control with lower dynamic. So these two algorithms, short-term and long-term prediction, will help to optimize the control of the fuel cell to increase the lifespan. So what just keep away message is that mixing a physics-based model together with neural network is really powerful, very promising. There is a lot to do still to find the best method and also the best training method to use hybridization of model and data. And also in the near future, we will investigate other kind of architectures than LSTM, for example, temporal convolutional network that are faster to converge and faster to train, and also somehow faster to operate as inference, and also perhaps implement attention mechanism to improve the accuracy. Thank you very much for your attention, and very sorry for all this software problem.
We are also really thankful to you, Vincent. Is there any question to Vincent? We had some good remarks from already from Jan.
I don't know if Artur or Maxim are in the teams. Maybe they can ask something, because this seems to be very related.
Both.
They are there.
Yeah, they are there.
I don't know if they have questions. That's another thing.
Vincent, what was the algorithm name? Temporal comparing to LSTM?
Yeah, we are exploring TCN, temporal convolutional network. So it's a CNN type, but adapted for 1D time series. So it operates convolution kernel.
Okay.
TCN, temporal convolutional
TCN.
network.
Okay. Thank you.
Yeah.
Thank you.
And it's proven to be very faster to train, because it's a CNN type, so it can be trained in parallel. So it's faster.
Okay, maybe during the acceleration phase, we can consider that. We can talk about it for the hardware acceleration phase of the teaming project, the productization, the network package later on, not now, of course. Once you prove that, maybe we can work on that for this, like the architecture, RISC-V architectures to implement in that work package.
Okay.
But
just to mention that we are launching, it's very first work, but we are launching an internship on the implementation of this algorithm that I presented on Google, the chip, I don't know the name again, Coral AI and Halo. You know that there are chips for running AI algorithms embedded. You know this chip, Coral AI?
Oh yeah, I heard. My interest on the EU pilot. There is a MLS chiplet coming up with ETS Zurich EU pilot project. So, but we can also explore that. No problem. I mean, we have time. So let's see.
Okay. Great.
Thank you for your presentation.
Okay, I don't have a question, but a remark about the importance of the physics-informed machine learning, because in all projects where the AI is used, data is a big problem. It's really hard to get the enough data and true data, but this physics-informed machine learning opens a new gateway towards having some data, because it relies on the physics model, maybe especially for the early stage career researchers, I mean, like Emre here today, they can be interested in this because this gives us the opportunity to generate some realistic data based on the physical models. So I think this is really useful. But the validation of this data in its reliability, these are still open topics that can be improved uh, by some researchers. But it's one of the core ideas of the project, and we are really grateful to CEA researcher, especially Vincent, to give us this inspiring presentation. We can continue this in the brainstorming session. We are quite behind the schedule, so let's have a 5-minute coffee break, or maybe break without coffee, I don't know. And then we can be here at